All right. The ocean is about 4 kilometers away. But here it is. Take a look at it. Here's one at NC State, my home school. Do you think there could be swales typical for a standard swale? All right. Part of the reason we see so many of them is they're very simple to design. Basically, we use the Manning's equation to design swales. All right, and I'll show you a quick example of that in just a little bit. Swales do improve pollutants a little bit, not a lot, but the reason they're used as much as they are is because you have to transport water anyway, right? You've got water up here, it's got to go down here. Why don't we just have it flow through a swale versus staying on a street or going into a concrete lined channel? All right. But swales, those that I just showed you, those are all very simple. And most of the time, vast majority of the time, the swales that go in the ground are in fact very simple. But there are some examples of innovations in swales that you can find. First of all, they can become wetlandy. The one on the right has a little bit of a wetland feature. I'll talk about that a little bit later. You can put an underdrain in them or under them. Often, if you put an underdrain under the swale to help promote infiltration, people will also import a fill media, all right, for the water to be drawn through. And then you can always add check dams, and you can see some examples of different types of check dams in this picture. So anything that you do to a swale like this would be expected to improve how well it works. So here's an example of a check dam. That's probably the simplest improvement that people will make to a swale. And the check dams usually are rock. They don't have to be, but they usually are rock. Here's some very pretty check dams from New Zealand. Okay. So I'm going to show you some examples of what this could look like. And this is a very broad, this one here is a very broad swale, but still very attractive. Here's where they have sort of boulder check dams, and they've created almost a step pool system in the art museum. And here's a more classic case that we would see of check dams for swales. All right. So everyone, by me showing these pictures, like, yep, I get it. Check dams. They block the flow to some extent, or certainly slow the flow down. Here's some more ultra urban ones, and this might be more of an example of a fit you'd have here in Rookie, where the water comes off the street and then it flows in these contained boxes, concrete boxes almost, for treatment. And you can see an example of a check dam there. Now, here's an example of a check dam where they have a relatively small orifice in the bottom of it. So what do you think happens here when you get a big storm? What do you think happens? What do you think that segment of the swale becomes? We talked about them yesterday. What 3 practices did we talk about yesterday? Let's name one of them. I heard wetland. Wetland, what's another one? So dry ponds. And I think what you're telling me is this is like a dry pond. That's correct. That's correct. That a temporary, for a big enough storm, a temporary fills up, ponds up behind the check dam, and then the water will drain out through the orifice. Okay, it is still a swale, but for big storms, it can become like a dry detention pond. The last one from yesterday, by the way, was a wet pond. All right, so you can do, and so we try to put SEMs in boxes. All right, like this is this type of SEM, but really there's lots of permutations of a stormwater control measure that you can make. Well, this is a swale, but it's a lot like a dry pond sometimes. All right. So what would you expect check dams to be able to do? What do y'all think? You put a check dam in. Why would someone put a check dam in? To make the swale look better? Agreed. It's not like They're not being put in because, oh, that's going to make the swale look good. So why do people put them in? What benefit? Because there's got to be a benefit. Because why would people invest the extra time and material? Okay, great. You nailed it. That you'll get some ponding. So you would promote some infiltration, okay? And then there's also a little bit of a flow retardance benefit, okay? So that's the reason. You create ponding, you can slow the flow down. If it's a really big storm, it doesn't matter, but for smaller storms, it does. And you get a little bit of infiltration. So we went ahead and we actually tested that to see, you know, this happens sometimes where you get the computer and it just, oh, it's back. Nope, it's spinning. Oh. So I can start it, but I have a feeling I mashed too many. It stopped. And then when it was frozen, I must have hit one button too many. So let's do that. All right, if I hit this button, is it still being played or do you need to? Okay, great. Thank you so much. Hopefully that won't happen again. If it does, I'll just let it sit there. All right, move this over here. All right. So you guys answered that question. Whoops. So we did a study where we took a swale and we added a couple of check dams to the swale to impede flow. All right. And we wanted to see, did we reduce runoff volumes? And did we have an impact on flow mitigation? And for that matter, if you pond water, what might also happen while that water is ponded with certain pollutants? Yes, you could get some sedimentation. All right. So this is what it looked like before we added the riprap check dams and after we added the rock check dams. It doesn't really look a lot different, does it? Because it's about the same. And so I'm going to share with you what we observed. And the biggest challenge that we had was that we had a small sample size here compared to a big sample size here. All right. But even with the small sample size, the big sample size, you can see that once we added the check dams, there was what appeared to be some additional benefit and volume mitigation. That means more water went into the ground. All right. It was not significant. If you take a look at flow rate, we had much bigger flow rates occur post install. So as a result, we can't really, I mean, they're going to be numbers, but it's a little too hard to compare. I mean, it looks a little bit better, but we also had bigger storms coming in. So that's kind of a warped statistic. But there's certainly one thing that held true is that the quality of the water after the check dam install from a sediment standpoint was certainly better. All right. And importantly, the inlet concentrations were comparable. All right. So while it's a little bit fuzzy, certainly it's very fuzzy about peak flow mitigation, we do have a decent sense there was more volume mitigation. There was some water going into the ground. And because the water was being ponded behind the check dams, we did see additional sedimentation occur. All right. Now, remember this, that if you're getting a benefit of the sedimentation, does the sediment disappear? No, right? It doesn't disappear. It just collects in front of the check dam. So what do you think that means if you are a maintenance professional? What if you're responsible for maintenance? So guess what you're going to have to do if you put check dams on your swales? You're going to have to remove the dirt sometimes. All right. That's just the nature of the beast. If a practice works better at removing pollution, let's stick with sediment, then you're going to have to clean your practice out more than normal, than you would have otherwise. All right. So just be mindful of that there's a maintenance need once you make this design improvement. All right. Now, from nitrogen standpoint, there was no change. Why do you think we didn't see any improvement? In fact, it got worse, but really, look at the effluent concentrations. The effluent concentrations are about the same. All right. So why do you think there was no real change pre and post check dams? Well, how do you get rid of nitrogen? You remember? See some answer. I'm going to come over here and hear what you have to say because I have a feeling you're right. What you think? So there could be dilution. Okay. Do you remember what the pollutant removal mechanism was to get rid of nitrogen? Denitrification. And what do you need for how quickly does denitrification happen? Does it happen in seconds? Nope, you're right. Does it happen in minutes? Nope. Does it happen in hours? Not really. Does it happen in days? Yes, it happens in days. The next question was going to be weeks, but you don't have to wait. You can get it done in days, okay? Days. So how long is water being ponded behind these little check dams? Maybe a little bit is being ponded for a while, but most of it isn't, right? Most of it is just temporarily there, and usually in hours, the water is gone, all right? So the reason there was no improvement in nitrogen is because we didn't give it enough time. It's just the system's not designed for it. I want everyone always to be mindful of that because one of the things that you're going to, as you go through your stormwater career, people are going to create devices to sell you, all right, or designs to sell you. You may even be the one creating the design to sell, all right? Just make sure that the claims they make sense, all right? Most of the time they do. They say this practice will remove cadmium or copper or lead, and they have a really rapid flowing media. Well, the water passes through at, 1,000 liters a second or 100 liters a second. Like the water just flows through real fast. You can get rid of lead or cadmium or copper. You can do it. You bet. If the media is right, the chemistry is right in the media, sure you can. If someone has that exact same media and says, and we can get rid of 40% of nitrogen, what's your reaction going to be? Well, that's a good reaction. Mine, in a polite way, I would be like, how? Well, that's cool. How? How's that going to happen? All right. That's why it's so important to really understand those pollutant removal mechanisms. That's why I gave an entire lecture just went to that because that's a fundamental behind stormwater control measure. Know that fundamental, know how hydrology can be transformed, all right, by soaking the ground, stretching, going in the atmosphere, and know how pollutants can be sequestered or changed or gobbled up, all right, preyed upon. All right, so there we go. So this is actually not a surprise. Plus, these are grass systems, grass dyes. There's accumulation of nitrogen actually in these things. So swales are not particularly good. Standard swales are not particularly good at nitrogen removal. All right, which gets us to the next category of swale, and that is the bioswale. Now, this practice, I think, does also have some potential to be used here in Roorkee and across India. Bioswales, and we're going to talk about bioretention at the very end of this lecture, the third lecture today, rather. But bioswales are a hybrid of bioretention, which is a fill media-based practice, all right, and swales. And essentially what you have is you see the under drain here, the gravel layer, and then they put a fill media, a specialized fill media, and then they sculpt the media like they want it, and then they put grass on it. That's what they did here. All right. Um, and so the water will not just flow along the surface, but will also be pulled through the media. All right. And get filtered. So here's an example of one where they didn't use grass. They were going to place a couple of plants in there, but they have a mulch covering on top, and you see the vegetation going. And you can see the media, the specialized media that lets the water pass through. Then they had a check dam to help pond water over it. All right. Then at the bottom, underneath all of this media, is an underdrain. All right. So that's what a bioswale looks like. What's nice about bioswales is they're long and narrow. Okay. So it's a long, narrow practice, which means it's able to fit into places that many other practices simply can't. All right. That's one of its big advantages. It fits into places that other practices simply can't. All right. So there are many bioswales. This practice was sort of naturally evolved. It was a natural evolution from standard swales, especially in places where bioretention gets used. So Seattle. Any of you guys have? In fact, I was intrigued that a number of the faculty here have. I think all of them were sons specifically that work in Seattle. This is where Microsoft is based. And for those of you that like coffee, it's the home of Starbucks. All right. So Seattle has a bunch of bioswales. This is in New Zealand, and this is their bioswale design guidance. And it's effectively like I just showed you. There would be some media here and under drain on the surface. You see the grass, and they also have a little check dam. So again, we have our design standard. You go look around like, oh, Auckland, New Zealand, almost the same design standard. That should make you feel pretty good, right? That different parts of the world are coming up with similarly inspired designs. This would be the North Carolina cross section. And again, you see a fill media, a specialized media that's brought in. You basically dig out a channel, put an under drain in, gravel, media on top. That's really all it is. And you can see it at work. Here's one where the water is flowing on the surface. You see this under drain right here? That pipe connects to the under drain underneath all the media, and here it is spilling out simultaneously. And oh, I think I have a video. Let's see if that works. Oh, yeah. This is the water coming out the under drain, and here's your water flowing over the top of the swale. And that is a bioswale in a nutshell. All right. Now, how well to bioswale? Oh, there's another one. Okay. Oh, I should also meant to point out they're used in Singapore. These are pretty cool. And this is a heavily vegetated one. Most of the ones I've showed you have been turf grass, but in places that get a lot of rain, like I'm going down tomorrow to Kerala. You know what I'm supposed to do every day when I'm in Kerala? Rain. Okay. So places that get a lot of rain, you can have a wide assortment of vegetation growing. Dry places, you're going to be more apt to have more desert plants growing. I've seen bioswales used in semi-arid North America, and they have a lot of rock and a few select plants in there. It's a good looking practice. So always remember, if you see a design in Singapore and you're trying to use it in Roorkee, that's probably not going to work right because it's a lot wetter there. If you see design from North Carolina plant-wise and you want to try it in Roorkee, probably not going to work right there either because we have rain throughout the year and you have a decently long dry spell plus a very wet period. So getting appropriately adapted plants is always a key with any of these biological practices. All right, there's one in Ohio. Now, we've monitored several bioswales because our Department of Transportation, or you might call it the Transportation Ministry, really is interested in using them. Why do you think our Department of Transportation would be so interested in using it? What is it about a bioswale that a highways department will be like, we should try that out? Why do you think that's the case? What type of landscapes do departments of transportation have to manage? Someone builds a road. Describe the parcels that they have to acquire and manage. Like, for example, would a Department of Transportation or a transport ministry manage a campus like all of Rookie, IIT? No, you're right, they wouldn't. So how do you describe the landscape that a Department of Transportation is managing? I'll give you two choices: round or long and narrow. You got it. Long and narrow. So if you're responsible for managing long and ribbony, okay, like a ribbon landscape, then you probably want to have a practice that can fit in along that long and narrow landscape. That's why departments of transportation are so. Do any of y'all work for a transportation ministry? Do you have any friends that do? A lot of people who study civil engineering will go to work in one of those ministries. It's a common place to go, all right? Because you know about roads, right? And you know about geotechnical problems, you know about water transportation. Those are all things that roadway designers and managers have to know, all right? So if any of you end up going to work with a roadway or government entity that manages roads, then this may be a practice you'll be using, all right? So here we go. So we monitored it, all right? We monitored water that had come off the road coming down this concrete swale. We collected samples right in here. And then we looked at the water that left by way of the underdrain, okay? And then we looked at the quality of the water that overflowed and went into the box. So we measured water quality right here, and we measured water quality right here, and then we picked up samples right in here. Is everyone clear? All right. So now I'm going to show you the results. The water that went out this under drain, okay, which meant it flowed through the media, all right, it was 88% cleaner than what entered. The water that stuck in the grass on the surface, it was only 10% cleaner than that which entered. Got it? So, do you think there's a benefit in having water flow through a media? Without question. Okay. And so, if you have a department of ministry, a transportation ministry, rather, Department of Transportation, they're going to probably, if they have to meet certain water quality standards, they're probably going to invest in something like this. All right. And then, as I may have alluded to earlier, but if you merge stormwater control measure amendments like check dams with bioswales, we have some tests that we eliminated all the runoff because all the water ponded up behind the check dam and flowed through the bioswale media, and all the surface flow was eliminated. The only flow we had, thank you so much, Nikhil, I appreciate. The only flow we had was, I love masala. I'm going to miss this. I'm going to miss a number of things about being here. So I am going to be very happy to be seeing my children, extremely happy to see my children. But I'm going to miss the masala chai, and it's going to make me want to come back to get more chai. If life was always so simple, right? Thank you for bringing that in. You can remove all flow, surface flow, which is pretty good. Now let's talk about wetland swales. Do you think there's a possibility for wetland swales in the area around Rookie? How many of you, show of hands, like, yeah, I can see wetland swales being used around Rookie. Let me help influence your vote. How many of you think that you could put wetland swales in and around Rookie? Every hand should go up because you have some wet areas around here. High water tables, all right? They're obviously generally flat. I'm very proud that none of you got wet while crossing, or if you did, you kept it quiet. That's fine too. But yeah, this is a great place for wetland swales. So guess what? Let's see what a wetland swale might look like. The biggest difference between them is that the water table is up at or very close to the surface. And as a result, you get wetland vegetation to grow. All right. You can see what's very clearly a wetland swale with a lot of typha, by the way, or tifa. And then a standard swale right over there. We actually monitored standard swales and we compared their water quality to wetland swales. All right, we had a pretty cool, this was an old project, and it was pretty cool. And see this green bar, that's the concentration of nitrogen leaving the standard swales. We had 4 of them that we studied. And these low green bars right here, that's the concentration of nitrogen leaving the wetland swales. How many of you are surprised that the wetland swales release lower nitrogen concentrations than standard swales? Well, I'm going to tell you why I wasn't surprised. What did we talk about in the pollutant removal lecture? We talked about denitrification. Denitrification occurs where you have aerobic zones and anaerobic or anoxic zones in close proximity. So wetlands provide that close proximity, right? A soil that gets saturated becomes anoxic relatively quickly. The root zones in and around the anoxic areas, they have oxygen. They're aerobic. So guess what? The ability for nitrogen to denitrify is much better in a wetland swale than it is in a standard swale. And that's why there's lower concentration. Most of the time, data makes sense. As y'all are doing your studies, if you've done, some of you are doing PhDs. Most of the time, data makes sense. There are some times you're like, that does not make sense. And either it's one of two things. Either there's a key fact you don't know, all right, and that does happen. Like, oh, I didn't know that. And that would explain it. Or the data are wrong because there was something you did in the monitoring that was wrong. Okay. The data almost always makes sense. All right. So if you see that, there's got to be a reason. And the reason is that it employs the right pollutant removal mechanisms. All right. So here's a series of wetlandy swales. They even added check dams to make the wetland swale wetter. Okay. And as I mentioned earlier, there is an additional benefit in addition to nitrogen removal, is that you can sequester carbon. We talked about that yesterday, where the dry swales sequestered less carbon than the wetland swales. All right. So there are benefits to having wetland swales. Now, if you want to learn more about or read more about the different types of swales that are out there, my colleague, Dr. Sujit Ekka, how many of you guys know Professor Sumit Sen here at Rookie? Well, Dr. Ekka and Professor Sen are good buddies, like really good buddies, all right? And so Dr. Ekka and I wrote this document. It is free. You don't even have to have a fancy Mahatma Gandhi library membership. You can get this sucker for free. All right, swell terminology for urban stormwater treatment. Okay, now let's talk a little bit about design. When we spoke about designing wetlands and permeable pavement and rainwater harvesting, when we did all of that, what was the storm that we were designing for? Like all those designs, we were checking it against what storm? Very good. I want everyone to remember, what's that number? 35 millimeters. I'm not going to give you that number, but you're going to have to know that number for your exam. All right, I'm just letting you know. You have to know that number for your exam because all water quality is based off that number. All right, there's a reason we spent the time on that on Monday afternoon. Okay. How do you design a swale for 35 millimeters of rain? Let me ask you this question. Can you realistically, or wait, no, actually, does it make sense for you to design a swale based on a rainfall depth of 35 millimeters? Thank you. The answer is no. It doesn't even make sense, right? Because are swales capturing volumes of runoff? No. They're transporting flows of runoff, right? The director would have been proud of you for that's what's happening. Director's gone, but I mean, oh, there she's in the back. So it's not reasonable, right? It's not reasonable to design for a ponding depth. So therefore, when we design swales, we are designing for not a rainfall depth, but what do you think? What would you guess we're designing for? If it's not a rainfall depth, what is it? I think you said intensity? Yeah. You're designing for rainfall intensity. That is correct. You want to come to North Carolina? You want to be a grad student at NC State? You're doing great. Okay. You design for a rainfall intensity. So then the question is, what intensity? All right. So we're going to have intensity be over here. Do you guys read my writing okay? Yes, thank you. And you ready for this? This is going to come as a shock to all of you. We'll call it intensity rank. So intensity in terms of millimeters per hour and intensity rank. Tell me if you've seen this before. You rank them from the tiniest little baby intensities to the really big intensities. The biggest intensities ever. The best intensities you've ever seen. You guys ever make fun of President Trump? He's very easy to tease. The best intensities ever. You've never seen such good rainfall intensities. All right, you guys don't have to laugh, it's fine. All right, so anyway, here we go. I'm just ranking my intensities. All right, pop, pop, pop. You can imagine me doing it. Here's your rainfall intensities. You do them by 15-minute periods if you can get that data. Hour increments if you must. All right. And then you integrate and you figure out where's the line where we have 80% or 90% of all rainfall intensities, so that we're only letting 10 to 20% bypass. All right. Whoops, that was a really lousy S. That's how you do it. Now, we did not go into that. We only had rainfall daily data. But even if you only have like a 5-year record of hourly data or 15, if you can get 15-minute data, that's better because swales are designed for smaller catchments, all right? But even the hourly data is a good start. You basically do the exact same thing, and then you figure out what that rainfall intensity is, all right? Some people would actually argue, and I can understand that, it depends on the practice, that instead of looking at the cutoff being here, that your cutoff should actually be a vertical cutoff. And then you would want to have 80% of your rainfall intensities be to the left of whatever this intensity needed to be. All right. So long story short, in North Carolina, we have our rainfall intensity being, our water quality rainfall intensity being 19 millimeters per hour. My hunch is that our numbers would be relatively similar because we both have very intense storms hit us. Okay. If I were, and why 19 and not 20? Because we don't design on 19. We design on 0.75 inches per hour. You can do the math, that's about 19 millimeters. All right. That's why it's not 20, right? 19 doesn't really make any sense, but 20 makes a lot of sense, 20 millimeters per hour. But we're designing based on 3/4 of an inch per hour. All right. Is this good or something bad? Something happened? Uh-oh. Dun, dun, dun. So that is how swale intensity, that's how rainfall intensities that you design for are determined for water quality purposes, right? If you're designing it for a big storm, then guess what you do? You look it up in your meteorological record, all right? They'll tell you the 10-year, thank you so much, the 10-year 5-minute intensity or the 10-year 10-minute intensity for rookie is blank, all right? And those numbers will tend to be actually a fair amount higher. I'm trying to think about the relationship. About 125 millimeters per hour, I would bet. Okay. So next, you've determined this intensity. We're not going to worry about what it is here, all right? If you want to make it 20 millimeters per hour, that's fine. But I'm not going to worry about it right now. Just understand that that's a calculation you go through and you make. Then you got to figure if I'm trying to remove any pollution from my rainfall, all right, and my flow, how long do I need to keep that water in the swale to expect to have some sediment in particular get removed? Well, we looked at it and came up with 4 minutes. All right. That number is probably pretty good for here too. It's not like soil particles are appreciably different. Dirt is dirt, right? If you have a heavily clay, where it's a lot more clay, then maybe the number needs to be bigger. But also at some point, you can just forget it because you're not really going to remove clays. All right. So 4 minutes is not a bad number to use. But, maybe some designs can go through and you can figure out what's better. But 4 minutes is a good amount of time. All right. So if you know you've got to keep your water in there for 4 minutes, then how long does your swale need to be? How long does your swale need to be? You got to keep your water in there for 4 minutes. How long does your swale need to be? You actually have all the tools to figure it out right now. All right? Maybe not to the exact number, but you know everything that you need to know to figure that number out. All right? And that is just a very simple equation. Okay, here we go. We know you got to keep the water in there for 4 minutes. We know we're going to have a flow rate. The flow rate, okay, is going to be based on, flow rate, you actually, Q equals VA, all right? You would calculate your flow rate. Your flow rate is based on your catchment. So do you guys use this equation? This is a runoff coefficient that ranges between 0 and 1. This is a rainfall intensity. And that's an area. Do you guys use that equation? Okay, great. So you basically calculate your flow rate based upon an intensity. North Carolina, that intensity happens to be 19 millimeters per hour, all right? And then whatever your runoff coefficient is, whatever your area is, you get your flow, you plug your flow in here, you divide through by your expected cross-sectional area, and all you got left is velocity, all right? So you've determined that velocity. Let's say that velocity ends up being let's say it ends up being 0.5 meters per second. See if that makes sense. Okay. 0.5 meters per second. You have to keep it in there for 4 minutes. Multiply that by 60 seconds by 4 minutes. That's a 60. Try again. 60 seconds by 4 minutes. What do you guys get for that? 120 meters? And there you go. Now, I just picked 0.5 meters per second as a flow rate. That may actually be a little too, as a velocity, that may be a little too high, all right? The point being is that's how you calculate your length. Did the thing crash again? Oh, no, we're good. Is it okay? It's a finicky machine today. It's already ghosted me once, and we've got this. All right, so everybody good on swale length? All right. Thank you, by the way. It's probably wise that you don't go too far away. Okay, now this is a really important question. How deep can you carry the water flow in your swale if you want it to remove pollutants? How deep can how deep can you allow the water to flow in your swale? Let's just go on, right? So that you remove pollutants. What's that? A subcritical, okay. That would be a possibility. It actually deals with a biological control. If you want to remove pollutants, you've got to basically force your water through as much friction as possible, right? If you reduce your friction, the water will flow faster and it's harder for the pollutants to get removed. Now, if it's a really big storm, you're trying to remove a big storm for flooding, then that's perfectly fine. We're going to get the water out of there. But if you're trying to remove pollutants, then you actually want to limit the height of your flow to the expected height of your grass, right? Because once the water overtops your grass, then the friction loss goes per flow rate goes down quite a bit. All right. So you want the water to flow through your grass and not over your grass. So, like, how high does your grass grow here? Maybe I should say how high can it grow? In North Carolina, that number is usually between 10 and 15 centimeters. All right, that's our grass growth. I wouldn't be surprised if you're roughly there here, maybe closer to 10. All right. So the answer is, how deep can your flow be when you're trying to remove pollutants? Now remember that, when you're trying to remove pollutants, and that number is, in North Carolina, we said 15 centimeters, but it says it may not exceed 15 centimeters. but sometimes we counsel our designers to use 10 centimeters in case that the grass that they're using to line the swale just doesn't get that tall. All right, so there you go. That's a very important consideration. You got to make sure you don't have the water overly tall, overly high, so that you don't overwhelm the grass. Now, side slopes, some folks refer to those as batter slopes. I know that's the term that's used in New Zealand, but you may have a batter slope, the side slope. We like to limit that to 3-to-1. That's because it's easier to maintain something on a 3-to-1 batter, a 3-to-1 side slope relative to something steeper. Crap, I thought I'd switch this over for you. Swales tend to be trapezoidal. Swales tend to be trapezoidal. And by that, I mean like this, boom. Well, let me try again. It's more like that. All right. That wasn't very good. This width right here is set to 2 meters. Okay. Does anyone any idea why the width the bottom width, like the widest you want that swale to be is 2 meters? I'll give you a hint. It's not, well, it probably is mathematical, but it's not like you're going to some equation. Kidding, it is a stinker today. What is it? You think, hey, don't make it, why don't you make it 6 meters? Why can't the bottom of a swale be 6 meters? Guess what? Because this, what do you think? Yeah, it deals with flow. It basically means, because of the road. Yeah, that's actually a really good reason. First of all, what road wants to have a 6 meter wide swale next to it? That's a lot of extra land to buy. That's a very good point. The other reason is that anecdotally, it is found that once you get a flow rate, this isn't 6 meters, but close to it. Once you get a swale bottom wider than this, then you start getting preferential flow paths inside that swale bottom. Okay? So then you're actually never using all 2 meters. In fact, we use 6 feet, which is almost 2 meters. I even say that most 6-foot wide swales or 2 meter wide swales don't quite work as intended. All right. So that's why that's an anecdotal observation. I'm sure someone that's highly powered in math could tell you why that happens. I'm not highly powered in math, but we do observe what actually goes on in there. So the bottom width is 6 feet or 2 meters. These side slopes here are 3-to-1. 3-to-1 side slope or more. And that trapezoidal is better than triangular, which probably isn't a surprise either. Okay, the high water table. If you're designing a standard swale, you do not want to hit your seasonally high water table. But what swale would be perfectly fine if you hit a seasonally high water table? What would you guess? There is a type of swale, the wetland swale. That's exactly right. Now, if you're designing a bioswale, then you need to have extra clearance between where you're putting that bioswale and the high water table, right? Because the bioswale has a filter media that's placed underneath it. So a standard swale, you have to avoid the water table. A wetland swale, you can hit the water table. You preferably hit the water table. And then a bioswale, you probably want your water table to be down a meter to be able to make it work. All right? It's not that different from what we talked about with permeable pavement, to be honest. The types of grass that you use needs to be firm. So when it goes up, you don't want it to be like lame-o grass. You push it over and it falls over. All right? You want that grass to be rigid so as the water flows, it doesn't bend it over. Now, I don't know what grass you would use for that, but I've got good news for you. There are people in India that do. And who I don't know where your closest agricultural university is, but they're going to have a grass specialist. And you can just ask that person, hey, what grass grows kind of tall and is rigid? And they should be able to, relatively rigid. And they should be able to answer that for you. And boom, that's the one you want to use. We talked about that. Um, I did mention that these same swales that are trying to improve water quality also need to be able to pass big storms without causing flooding. So your 10-year rainfall intensity, that may be 150, it might be 250 millimeters per hour rainfall rate. That's very intense, but I would bet that during the monsoons, you get some really intense rainfalls. You got to be able to make sure your swale also carries that. Now, here's the deal. That's not that much of an ask. If you're restricting your water depth here, all right, to be 10 centimeters, then if a really big storm comes, then all you do is pond water above 10 centimeters. So maybe you need a half a meter to carry, or maybe even more, to carry the 10-year storm. All right. So the 10-year, maybe 10-minute intensity needs to be carried above the swale. All right. So that means if you're trying to convey, does it keep breaking? Or is it still okay? If you're trying to convey big storms, you just need to make sure that your swale is sufficiently deep. Okay? That's all. It's not that hard. You just got to sink it. And that calculation is based off Manning's. Everyone familiar with the Manning's equation? Great. I'm not going to go through it because of time. I'm just going to assume that y'all know the Manning's equation. Okay. All right, next. Let's say you're designing a bioswale. Well, oh no, let's make it a little bit easier. Let's say you're designing a wetland swale. Well, if you're designing a wetland swale, then your practice is part swale and part what? Wetland. Part swale and part wetland. And so what our design guidance says is once you've done all your swale design, look to wetland design and inform the balance of your wetland swale design. All right. So that would be perhaps things like plant selection. You could do that in plant selection, or how densely you should plant your vegetation. All right. So instead of like recreating new design guidance specifically for wetland swales, our government agency says just use what we've said for wetlands, or just use what we've said for bioretention if you're designing a bioswale. All right. So that's what that says. Nothing super fancy. And then I think the last thing that they talk about here is having freeboard. Oh, darn it. Again, I forgot to make this SI. But having 15 centimeters of freeboard. So basically we're saying, hey, if you have screwed up your calculation, if you've made a little mistake, this is to help cover your rear end. Just add 6 more inches or 15 more centimeters and you should be good. All right. Another way to look at it is you got all your calculations perfect, but we think that 20 years from now, the 10-year storm is going to be more intense because of climate change. So we're going to give you we want you to put in another 15 centimeters of depth over there to make sure we can handle our future climate. All right. Either one is a good reason. So with that, What do you think, Professor Benarossi? You ready to put some swales in on campus? I know you are. She's ready. All right. Y'all have any questions about swales? Okay, what we're going to do is we're going to take a couple of breaks this morning. The first one's going to be short, 10 minutes. So literally, y'all look at your clock. It's 10:40 according to mine. 10:40, and she's a pretty lady. She said, "When you coming home, Bill?" I'm like, "A few more days, honey, a few more days." At 10:50, we'll start back up, okay? I'll see you at 10:50. We're going to talk green roofs. Hopefully, the next